Below in this lecture we'll answer two questions. In the first question we'll find out the size of this angle ABC is equals to x. We have to find out the value of this angle x. And in the second question we'll find out the length of this side AD is equals to x. So we have to find out the value of line segment x. So we start with the first question. In the drawing we have quadrilateral ABCD. Those two angles are both equal to 80 degrees in their sizes. We also know that PA equals to AD equals to CB. So we define BC as A. And then BA and AD be also equal to A because they are equal to each other. Again, our task is to find out the size of this angle ABC is equals to x. We have to find out the value of this angle and angle x. So first of all, we will join points B and D together by straight line. By joining points B and D, we divided this quadrilateral ABC into two triangles. This is the upper triangle BCD, and this is the lower triangle, triangle BAD. So in the next step, we'll focus on this lower triangle, triangle BAD. This lower triangle BAD, those two sides are equal to each other in their lengths. And we have the rule that says that in front of equal sides in the triangle, there are equal angles. And again, in front of equal sides in the triangle, there are equal angles. So in triangle BAD, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because according to the rule that I mentioned. We also know that the sum of the angles in any triangle is equal to 180 degrees. So in triangle BAD, alpha plus alpha is 2 alpha plus 80 degrees, in total must be equal to 180 degrees. Then again, in the lower triangle BAD, 2 alpha plus 80 degrees, in total the sum of those three angles must be equal to 180 degrees. Alpha plus 80 degrees equals to 180 degrees in triangle BAD. Here we'll subtract 80 degrees from this equation and we get that 2 alpha equals to 180 degrees minus 80 degrees is 100 degrees. 2 alpha equals to 100 degrees. Here we'll divide this equation by 2 and finally we get that the missing angle alpha equals to 100 degrees over 2 is 50 degrees. Those two angles are both equal to alpha, therefore each of them is equal to 50 degrees in size. What is the size of this angle BDC? From the drawings it's very easy to see that the size of this angle BDC equals to 80 degrees minus 50 degrees. 80 degrees minus 50 degrees is 30 degrees. So the size of angle BDC equals to 30 degrees. The next step, we define angle BCD. This angle is beta. And we focus on triangle BAD. Actually, we will implement the law of sines in this triangle BAD. Repeat quickly on the law of sines. The law of sines is true in any triangle. This is triangle ABC that could be any triangle. The length of this angle BAC is capital A degrees. This is angle ABC that is equals to capital D degrees in its size. Again, angle ABC equals to capital B degrees in its size. This is angle ACB that is equals to capital C degrees in its size. Likewise, side AB equals to 3 units in its length, side AC equals to B units in its length, side BA equals to A units in its length. This triangle ABC that could be any triangle according to the law of sines. The following equation is to A over sinus A equals to B over sinus B equals to C over sinus C. Again, this triangle ABC according to the law of sines. The following equation is to A over sinus A equals to B over sinus B equals to C over sinus C. So we can actually implement the law of sines in our drawing. We will implement the law of sines in this triangle BAD. Again, we implement the law of sines in this triangle BAD. According to the law of sines, in this triangle BAD, BD of sinus 80 degrees equals to BA over sinus 50 degrees. Repeat again, this triangle BAD according to the law of sines. The following equation is true. BD over sinus 80 degrees equals to BA over sinus 50 degrees. BA equals to A according to the definition, so we substitute BA by A. And we substitute 80 degrees by 2 times 40 degrees. And also substitute 50 degrees by 90 degrees minus 40 degrees. And we get that BD is the missing side, so we leave it as it is. BD over sinus 80 degrees. So sinus 80 degrees is sinus 2 times 40 degrees. And it is equals to BA. BA equals to A according to our definition over sinus 50 degrees. Sinus 50 degrees is sinus 90 degrees minus 40 degrees. So in total, we should find out that according to the law of sines, BD over sinus 2 times 40 degrees equals to A over sinus 90 degrees minus 40 degrees. In the next step, I will present to you two trigonometric identities, and we will implement the two new trigonometric identities in this equation. The first trigonometric identity is as follows. Sinus 2 alpha equals to 2 times sinus alpha cosine alpha. And the second trigonometric identity is as follows. Sinus 90 degrees minus alpha equals to cosine alpha. According to the first trigonometric identity, that is to say, sinus to alpha equals to 2 times sinus alpha cosine alpha. Sinus 2 times 40 degrees equals to 2 times sinus 40 degrees times cosine 40 degrees. And again, according to this trigonometric identity, sinus 2 times 40 degrees equals to 2 times sinus 40 degrees cosine 40 degrees. And it equals to A over sinus 90 degrees minus 40 degrees. According to this, the second trigonometric identity, that is to say sinus 90 degrees minus alpha equals to cosine alpha, we get that sinus 90 degrees minus 40 degrees equals to cosine 40 degrees. So in total, we should find out that BD over 2 times sinus 40 degrees cosine 40 degrees equals to A over cosine 40 degrees. Here we have cosine 40 degrees on both sides of this equation, so cosine 40 degrees will get cancelled. After cancelling cosine 40 degrees, in this side of the equation we left with BD over 2 times sinus 40 degrees. Well, on the other side of the equation, this side we left only with A. So in total, we should find out that BD over 2 times sinus 40 degrees equals to A. Here we will multiply this equation by 2 times sinus 40 degrees. And we will get that the missing side BD is equal to 2A times sinus 40 degrees. So actually, this is the missing side BD, that is equals to 2A times sinus 40 degrees in its length. So write it down. In the next step, we will implement the law of sines in this triangle BCD. According to the law of sines, in this triangle BCD, the following equation is true. BC over sinus 30 degrees equals to BD over sinus beta. Repeat again, according to the law of sines, this upper triangle BCD, the following equation is true. BC over sinus 30 degrees equals to BD over sinus beta. BC equals to A over sinus 30 degrees. Sinus 30 degrees is 1/2. So in total, in this side of the equation, we have A over 1/2 equals to BD. We already found out that BD equals to 2A times sinus 40 degrees. Over sinus beta. Sinus beta is the missing again, so we leave it as it is. So in total, we found out that according to the law of sines, triangle BCD, A over 1 half equals to 2A sinus 40 degrees over sinus beta. A over 1 half is 2A equals to 2A sinus beta, 2A sinus 40 degrees over sinus beta. So if you found out that 2A equals to 2A sinus 40 degrees over sinus beta. Here we have 2A on both sides of this equation, so 2A will get cancelled. After we cancel 2A, inside of the equation we have 1, 2A over 2A is 1, while on the other side of the equation we are left with sinus 40 degrees over sinus beta. Here we multiply this equation by sinus beta, and finally get that sinus beta equals to sinus 40 degrees. Sinus beta equals to sinus 40 degrees. If sinus beta equals to sinus 40 degrees, it means that beta equals to 40 degrees. This is the first solution for beta. But we have another solution for beta according to the third trigonometric identity. Sinus alpha equals to sinus 180 degrees minus alpha. So according to this third trigonometric identity, sinus 40 degrees equals to sinus 180 degrees. Here. According to the third trigonometric identity, sinus alpha equals to sinus 180 degrees minus alpha. So according to this trigonometric identity, sinus alpha equals to sinus 180 degrees minus alpha, we will get that sinus 40 degrees equals to sinus 180 degrees minus 40 degrees. So sinus 40 degrees equals to 180 degrees minus 40 degrees is 140 degrees. So sinus 40 degrees equals to sinus 140 degrees. We already found out that sinus beta equals to sinus 40 degrees. And we just right now found out that sinus 40 degrees equals to sinus 140 degrees. So we can write here that sinus 40 degrees equals to sinus 140 degrees. And from this equation, sinus beta equals to sinus 40 degrees equals to sinus 140 degrees. We derive that sinus beta equals to sinus 140 degrees. Those two sides of the equation are equal to each other. So if you found out that sinus beta also equals to sinus 140 degrees. If sinus beta equals to sinus 140 degrees, it means that beta equals to 140 degrees. This is the second solution for beta. The first solution for beta is beta equals to 40 degrees. So we have two solutions for beta. Beta could be equal to either 40 degrees or to 140 degrees. But if you focus on our drawing, here, focus on this drawing, in this green upper triangle BCD, this angle BCD is equals to beta. from the drawing, it is very easy to see that angle beta is definitely greater than 90 degrees. Again, angle beta is definitely greater than 90 degrees, and therefore, if angle beta is greater than 90 degrees, angle beta could never be equal to 40 degrees, that is less than 90 degrees. So we will cancel the first solution for beta, and we will take into account only the second solution for beta, that is actually beta equals to 140 degrees in its size. This angle BCD is equal to beta, is equal to 140 degrees in its size. We know that the sum of the angles in any triangle is equal to 180 degrees. So the sum of the angles in the green upper triangle BCD must be equal to 180 degrees. So which angles we have in this upper green triangle BCD? This angle equals to 30 degrees in size, plus this angle beta is equals to 140 degrees in size, plus this third angle, this is actually angle DBC. In total, the sum of those angles must be equal to 180 degrees, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Degrees plus 140 degrees is 170 degrees, so 170 degrees plus the missing angle DBC in total must be equal to 180 degrees. Here we will subtract 170 degrees from this equation. And finally, we will get that the missing angle DBC is equal to 180 degrees minus 170 degrees is 10 degrees. This is the missing angle DBC, that is equal to 10 degrees in size. Our task is to find out the size of this big angle, angle ABC. We have to find out the size of this angle, angle ABC. From the drawing, it is very easy to see that angle ABC is equal to x is equal to 50 degrees plus 10 degrees, that is 60 degrees. So we can find out that the angle that we are looking for, this question that actually the big angle ABC, that is also is defined as angle x, is equal to 60 degrees in size. Then again, this is the big missing angle ABC, this also equals to x, is equal to, in total to 60 degrees in size. So we finish with the first question. In the next step, I will present you the second question, and we will solve the second question by using two different methods. Our task in the second question is to find out the length of this side AD that equals to x. We have to find out the length of line segment x that equals to AD. So, first of all, so in the drawing we have quadrilateral ABCD. We know that AB equals to BP. This is the short line segment DP is equals to 1 unit sinus length. This is line segment PC, is equals to 4 unit sinus length. Those two angles are both right angles. Again, our task is to find out the length of this side AD is equals to x. We have to find out the length of line segment x is equals to AD. So first of all, we will join points B and D together by straight line. By joining points B and D, we divided this quadrilateral ABCD into two right angles. This is the upper right angle ABD, and this is the lower right angle triangle BCD. So in the next step, we will implement the Pythagoras theorem on those two right angles. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. And again, according to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So first of all, we will implement the Pythagoras theorem on this right upper triangle, triangle ABD. Here by PT is a version for Pythagoras theorem. In this upper right triangle, triangle ABD, according to the Pythagoras theorem, BD squared, that is the square of the hypotenuse, equals to AB squared plus AD squared. Repeat again, in this upper right triangle ABD, according to the Pythagoras theorem, BD squared, that is the square of the hypotenuse, equals to AB squared plus AD squared. BD is the missing hypotenuse, so we leave it as it is. It is BD squared equals to AB squared. AB is also the missing side, so we leave it as it is. AB squared plus AD squared. AD is x, therefore AD squared is x squared. X is the line segment that we are looking for in this question. We have to find out the length of line segment x is equals to AD. So in total, according to equation 1, we actually found out that BD squared equals to AB squared plus x squared. In the next step, we represent the Pythagoras theorem on this lower right triangle, triangle BDC. In this lower right triangle, triangle BDC, according to the Pythagoras theorem, BD squared, that is the square of the hypotenuse, equals to BC squared plus CD squared. And again, according to the Pythagoras theorem, in this right triangle BDC, the right lower triangle BDC, the following equation is to BD squared, that is the square of the hypotenuse, equals to BC squared plus CD squared. BD is the missing hypotenuse, so we leave it as it is. It is BD squared equals to BC squared. BC is also the missing side, so we leave it as it is. It is BC squared plus CD squared. CD in total equals to 1 plus 4, that is 5, therefore CD squared equals to 5 squared, that is 25. So in total, according to equation 2, we actually found out that BD squared, that is the square of the hypotenuse, equals to BC squared plus 25. This is according to equation 2, while according to equation 1, we have already found out that bd squared equals to ab squared plus x squared. So we have two different equations for bd squared. Equation 1 and equation 2. Therefore, we will create equation 3 that says that bd squared according to equation 1 must be equal to bd squared according to equation 2. Repeat again. Equation 3 states that bd squared according to equation 1 must be equal to bd squared according to equation 2. bd squared according to equation 1 equals to ab squared plus x squared. And it must be equal to bd squared according to equation 2. bd squared according to equation 2 equals to bc squared plus 25. So in total, according to equation 3, we found out that ab squared plus x squared equals to bc squared plus 25. In the next step, we will implement the product theorem on this green right triangle triangle PBC. According to the product theorem on this green right triangle PBC, PB squared, that is the square of the hypotenuse, equals to BC squared plus PC squared. Repeat again, according to the product theorem, on this right triangle PBC, the following equation is true. PB squared, that is the square of the hypotenuse, equals to BC squared plus PC squared. This gives us the question that PB equals to AB. Therefore, we can substitute PB in this equation 4 by AB. PB equals to AB, therefore PB squared equals to AB squared. And it equals to BC squared plus PC squared. So in total, according to equation 4, we have found out that AB squared equals to BC squared plus PC squared. PC equals to 4, therefore PC squared is 4 squared, it is 16. So in total, according to equation 4, we actually found out that AB squared equals to BC squared plus 16. This is according to equation 4, while according to equation 3, we already found out that AB squared plus x squared equals to BC squared plus 25. But according to equation 4, AB squared equals to BC squared plus 16. Therefore, we can substitute AB squared in equation 3 by BC squared plus 16. We will do it now, and we get that according to equation 3, we get AB squared is BC squared plus 16. And we have in equation 3 here plus x squared equals to BC squared plus 25. So in total, according to equation 3, we have found out that BC squared plus 16 plus x squared equals to BC squared plus 25. Here we have BC squared on both sides of this equation, so BC squared gets cancelled. After we cancel BC squared, on this side of the equation we left with 16 plus x squared On the other side of this equation, we left only 25. So in total, we should find out that 16 plus x squared equals to 25. Here we will subtract 16 from this equation. And when you get that x squared equals to 25 minus 16 is 9. X squared equals to 9. Here we'll take out of this equation. When we get that the missing 97x, that is the 97 that we are looking for, equals to the square root of 9, that is 3. So actually, 97 AD or side AD, that equals to x is equals to 3 units in its length. And again, this is 97 AD, that equals to x, and it equals to 3 units in its length. So we finish with the first method. In the next step, I present to you how to find out the length of 97 AD is equals to x according to the second method. In the second method, we will do a construction, that is to say, we will extend side DC of this quadrilateral ABCD by 4 units. Repeat again, we will extend this side DC of this quadrilateral ABCD by 4 units. And we will define the edge of this extended line segment DC. This point is point Q. And again, we define the edge of the extended line segment DC. This point is point Q. So according to our construction, CQ equals to 4 units. We extended line segment DC by 4 units, therefore CQ must be equal to 4 units according to our construction. This is side DC. This is one side of this quadrilateral ABCD. So side DC is the side of a quadrilateral. It is absolutely a straight line. When we extend the straight line by straight line, the result DQ is also a straight line. So DQ is a straight line. If we focus on the upper side of this straight line DQ at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of this straight line DQ at point C? We have this angle, that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will join points B and Q together by a straight line. By joining points B and Q, we can do the right triangle BCQ. This is the right triangle BCQ. So in the next step, we will prove that those two right triangles can go into each other according to side angle side rule. That is to say, we will prove that this is the right triangle PBC, that it can go into this right triangle BCQ. So we have to prove that the right triangle PBC can go into this right triangle BCQ according to side angle side rule. So why those two right triangles can go into each other? first of all, PC equals to CQ equals to 4. Those two sides are both equal to 4, therefore they are equal to each other. So I write it down. This is side PC, on the right hand PBC. This equals to this side CQ, on the right hand BCQ. Repeat again. Side PC on the right hand PBC equals to side CQ on the right hand BCQ. They are both equal to 4, and therefore they are equal to each other. In addition, those two angles are both right angles, and therefore they are equal to each other. So here, this is angle BCP. On the right triangle PBC, and it is equal to this angle. There's a angle BCQ. On the right triangle BQC. Repeat again, we should find out that angle BCP on the right triangle BBC equals to angle BCQ on the right triangle BCQ. They are both equal to 90 degrees, and therefore they are equal to each other. And finally, this is side BC. It is a common side that belongs to both triangles. So we can write down that BC equals to itself is a common side that belongs to both triangles. BC equals to itself is a common side that belongs to both triangles. So if we prove that those two right triangles can go into each other according to side angle side rule. Write it down. We prove that the right triangle PBC congruent, this is the side of congruent, to the right triangle BCQ according to side angle side rule. That is to say, we can prove that those two sides and the angle that is included between those two sides of this right triangle BCP are corresponding equal to those two sides, and the angle that is included between those two sides, this right triangle BCQ. And therefore, those two right triangles can go into each other according to side angle side rule. Repeat again, we have those two sides, and the angle that is included between those two sides, this right triangle PBC are corresponding equal to those two sides, and the angle that is included between those two sides, this right triangle BCQ. And therefore, those two right triangles can go into each other according to side angle side rule. And from the fact that those two right triangles can go into each other, we will derive that their corresponding sides must be also equal to each other in their lengths. The two corresponding sides of those two right triangles are those two hypotenuses, the hypotenuse BC and the hypotenuse BQ. So BC equals to BQ. BC equals to BQ. BC equals to BQ according to the rule that says that corresponding sides and congruent triangles are equal to each other. Those two right triangles can go into each other, and therefore those two their corresponding sides, that is to say BP and BQ, must be also equal to each other in their lengths. But according to what is given as a question, AB equals to BP. And again, according to what is given as a question, AB equals to BP. So we can write that AB equals to BP. AB equals to BP according to what is given as a question. And for this equation, AB equals to BP equals to BQ, we will derive that those two sides are all equal to each other in their lengths. AB equals to BB equals to BQ. So in the next step, we will do a construction. That is to say, we will draw a circle around point B in such a way that point B will be the center of the circle and BA will be the radius of the circle. Repeat again, we will draw a circle around point B in such a way that point B will be the center of the circle and BA will be the radius of the circle. As you can see, point B is the center of the circle and BA is the radius of this circle. So we define the radius of this circle as R. So BA equals to R, it is the radius of the circle according to our construction. But because of the fact that we already found out that AB equals to BP equals to BQ, BP and BQ must be also the radius of the circle is equals to R. What is the definition of a radius of a circle? The radius of any circle starts from the center of the circle and that's at the point of the circle itself. So point A is located on the circle itself. Well, this circle passes through point A. For the same reason, this circle must pass from point P and from point Q. So we can write down that the circle passes through points A, P and Q. The circle that we constructed passes through points A, P and Q. According to what is given as a question, this angle DAB, this is a right angle. Angle DAB is a right angle. If angle DAB is a right angle, it means that DA is perpendicular to AB. DA is perpendicular to AB, because DAB is a right angle. DA is perpendicular to AB. This is the sign of perpendicular. DA is perpendicular to AB, but according to our definition, AB is the radius of the circle. AB is the radius of the circle is equal to R. So in total, we found out that DA is perpendicular to the radius R of the circle. DA is perpendicular to AB, that is the radius of the circle. This is 978, it is perpendicular to the radius AB of this circle. And therefore DA is a tangent to this circle at point A. So write it down. DA is a tangent to the circle at point A. Here is the tangent of the circle at this point, point A. Point A is the point of tendency of tangent DA with this circle. So here we can implement tangent secant theorem. If we focus at point D, we can implement here tangent secant theorem. So repeat quickly on tangent secant theorem. According to tangent secant theorem, if a tangent and the secant are drawn to a circle from the same external point, point P. This is the common external point, point P. From this common external point, point P, we have tangent PA, that is tangent to this circle is point A. Likewise, from the same common external point, point P, we have secant PC that cuts this circle, those 2 points, B and C. PB is the external part of this secant, and the length of the secant in total is PC. Again, PC is the length of this secant in total, and PB is the external part of secant PC. And according to tangent secant theorem, the following equation is true. The square of the tangent lengths equals to the product of the secant's whole length and its external part. Or tangent squared equals to the external part of the secant times the whole part of the secant. Or in other words, PA equals to PB times PC. PA is the length of tangent of this tangent. Therefore, PA squared is the square of the tangent, PA, and it equals to the product of the external part of this secant, that is PB, times the length of the secant in total, that is PC. Or PB times PC equals to PA squared. Again, PA squared equals to PB times PC. Okay. So we can actually implement tangent secant theorem in our drawing. In our drawing, if we focus on this common external point, point D, from this common external point, point D, we have tangent dA to this secant, the tangent to this secant, point A. Likewise, from the same common external point, point D, we have secant dQ. The external part of secant dQ is dP, and the secant in total equals to dQ. The length of tangent squared is dA squared, and is equals to the product of the external part of the secant, that is dP, times the length of the secant in total, that is dQ. So dP times dQ equals to AD squared. Or AD squared equals to dP times dQ according to tangent secant theorem. So I write it down. If we focus on the common external point, point D, from the common external point, point D, we have tangent dA, that is tangent to this secant, point A, and we have secant dQ. The external part of secant dQ is dP, and the length of the secant in total is dQ. According to tangent secant theorem, the length of this tangent squared, that is dA squared, equals to the product of the external part times the length of the secant, that is dQ. The external part is dP, the length of the secant in total is dQ. So in the product between the external part to the length of the secant in total is dP times dQ. So in total, if you found out that dA squared equals to dP times dQ according to tangent secant theorem. Okay, again, according to tangent secant theorem, if we focus on the common external point, point D, the following equation is true. dA squared equals to dP times dQ. dA is x, therefore dA squared is x squared, and it equals to dP. dP is 1 times dQ. dQ in total it is 1 plus 4 plus 4, that is 9. So in total we should found out that x squared equals to 1 times 9, that is 9. X squared equals to 9. Here we take out of this equation, and finally we get that x equals to the square root of 9, that is 3. X equals to 3. Actually, the length of this last segment AD is equals to x is equal to 3 units. So actually, in both methods, we found out that the length of this last segment AD is equals to x is equal to 3 units. So we finish with the second method of the second question. In the next step of some other lecture, that is to say, we repeat on the solution of the first question, and then we repeat on the solution of this second question on both methods. Our task in the first question was to find out the size of this angle ABC is equal to x. We had to find out the value of this angle, angle x. So in the domain we have quadrilateral ABCD. Those two angles are both equal to 80 degrees in their sizes. In addition, we know that AB equals to AD equals to BC. Again, our task is to find out the size of this angle ABC is equals to x. We have to find out the value of angle x. So first of all, we join points B and D together by a straight line. By joining points B and D, we divided this quadrilateral ABCD into two parts. The first part is the green right triangle BCD, and the second part is this right triangle BAD. We know that BC equals to BA equals to AD. So if we define the length of BCSA, then BA and AD must be also equal to A because they are equal to each other. So in the next step, we focus on this triangle ABD. Those two sides, this triangle ABD, are equal to each other in their lengths, according to what is given us the equation. And we have a rule that says that in front of equal sides in the triangle, there are equal angles. Again, in front of equal sides in the triangle, there are equal angles. So in this triangle ABD, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to all the dimensions. We also know that the sum of the angles in the triangle is equal to 180 degrees. So in triangle ABD, alpha plus alpha is 2 alpha plus 80 degrees, in total must be equal to 180 degrees. In triangle ABD, the sum of the angles must be equal to 180 degrees, that is to say 2 alpha plus 80 degrees, in total must be equal to 180 degrees. If we subtract the 80 degrees from this equation, if I found out that 2 alpha equals to 180 degrees minus 80 degrees is 100 degrees. 100 degrees. So 2 alpha equals to 100 degrees. If we divide this equation by 2, if I found out that the missing angle alpha equals to 100 degrees over 2 is 50 degrees. So those two angles are both equal to alpha, and therefore each of them is equal to 50 degrees in its size. What is the size of this missing angle BDC? From the dome it is very easy to see that angle BDC equals to 80 degrees minus 50 degrees, that is 30 degrees. The next step, we define this angle BCD as beta, and then we implemented the law of sines in this triangle ABD. So repeat quickly on the law of sines. First of all, the law of sines is true in any triangle. This is triangle ABC that could be any triangle. The size of this angle BAC is capital A degrees. The size of this angle ACB is capital C degrees. And the size of this angle ABC is capital B degrees. Likewise, the length of side AB is C, the length of side AC is B, and the length of side BC is A. So in this triangle, we see that could be any triangle according to the law of sines. The following equation is to A over sinus A equals to B over sinus B equals to C over sinus C. Again, according to the law of sines, in this triangle ABC, the following equation is to A over sinus A equals to B over sinus B equals to C over sinus C. So we can actually implement the law of sines in our triangle BAD. We implemented the law of sines in this triangle ABD. According to the law of sines, this triangle ABD, BD over sinus 80 degrees equals to BA over sinus 50 degrees. Again, BD over sinus 80 degrees equals to BA over sinus 50 degrees. Triangle BAD, according to the law of sines, BD over sinus 80 degrees equals to BA over sinus 50 degrees. BA equals to A, so we substitute BA by A. We substitute 80 degrees by 2 times 40 degrees, and we substitute 50 degrees by 90 degrees minus 40 degrees. So in total, if we found out that BD over sinus 2 times 40 degrees, that is 80 degrees, equals to A over sinus 90 degrees minus 40 degrees, that is 50 degrees. And BD over sinus 2 times 40 degrees equals to A over sinus 90 degrees minus 40 degrees. Then I presented to you two trigonometric identities and implemented those two trigonometric identities in this equation. The first trigonometric identity is sinus to alpha equals to 2 times sinus alpha cosine alpha. The second trigonometric identity is sinus 90 degrees minus alpha equals to cosine alpha. According to this first trigonometric identity, we will get that sinus 2 times 40 degrees equals to 2 times sinus 40 degrees times cosine 40 degrees. Likewise, according to the second trigonometric identity, sinus 90 degrees minus alpha equals to cosine alpha, we get that sinus 90 degrees minus 40 degrees equals to cosine 40 degrees. So in total, we found out that BD over 2 times sinus 40 degrees cosine 40 degrees equals to A over cosine 40 degrees. Here we have cosine 40 degrees on both sides of this equation, so cosine 40 degrees will get cancelled. After we cancel cosine 40 degrees, in this side of the equation we left only B5, while on the other side of the equation we left to be BD over 2 times sinus 40 degrees. And again, in total, we found out that BD over 2 times sinus 40 degrees, BD over 2 times sinus 40 degrees equals to A. Here we multiplied this equation by 2 times sinus 40 degrees, and finally found out that the missing side BD equals to 2A times sinus 40 degrees. This is the missing side BD, that equals to 2A times sinus 40 degrees in its length. In the next step, we implemented the law of sines in this triangle BCD. According to the law of sines, in this green triangle BCD, the following equation is to BC over sinus 40 degrees equals to BD over sinus beta. Again, BC over sinus 40 degrees equals to BD over sinus beta. And again, upper triangle BCD, according to the law of sines, BC over sinus 40 degrees equals to BD over sinus beta. BC equals to A, and we already found out that BD equals to 2A times sinus 40 degrees. So BD over sinus 40 degrees equals to BC over sinus 40 degrees equals to BD over sinus beta. Actually, BC is A, so it is A over sinus 40 degrees. Sinus 40 degrees is 1/2. So in total, in this equation, we have A over 1/2 equals to, again, BD is 2A times sinus 40 degrees here over sinus beta. Sinus beta is the missing side, so left it as it is. In total, we found out that A over 1/2 equals to 2A sinus 40 degrees over sinus beta. A over 1/2 is 2A, and it equals to 2A sinus 40 degrees over sinus beta. Here we have 2A on both sides of the equation, so 2A will get cancelled. After we cancel 2A, in this side of the equation we left with 1. 2A over 2A is 1. While on the other side of the equation we left with sinus 40 degrees over sinus beta. So in total we found out that 1 equals to sinus 40 degrees or sinus beta. Here we multiply this equation by sinus beta, and we can find out that sinus beta equals to sinus 40 degrees. Found out already that sinus beta equals to sinus 40 degrees. If sinus beta equals to sinus 40 degrees, it means that beta equals to 40 degrees in size. But we have another solution for the value of angle beta, for the size of angle beta. According to the first trigonometric identity, sinus alpha equals to sinus 180 degrees minus alpha. So according to this first trigonometric identity, we will get that sinus 40 degrees equals to sinus 180 degrees minus 40 degrees. So sinus 40 degrees equals to 180 degrees minus 40 degrees is 140 degrees. So in total we should find out that sinus 40 degrees equals to sinus 140 degrees. But we already found out that sinus beta equals to sinus 40 degrees. And sinus 40 degrees equals to sinus 140 degrees. So we copy this equation here. Sinus 40 degrees equals to sinus 140 degrees. And for this equation, sinus beta equals to sinus 40 degrees equals to sinus 140 degrees. We have that those two sides of the equation are equal to each other. That is to say, sinus beta equals to sinus 140 degrees. If sinus beta equals to sinus 140 degrees, it means that beta equals to 140 degrees in size. This is the second solution for beta, but according to the first solution for beta, beta equals to 40 degrees. So we have two solutions for beta. Beta could be equal to either 40 degrees or to 140 degrees. But if we focus on our drawing, this green triangle BCD, this is angle beta. It is very easy to see that angle beta is definitely greater than 90 degrees. If angle beta is greater than 90 degrees, angle beta could never be equal to 40 degrees. That is less than 90 degrees. So we consider the first solution for beta, and we took into account only the second solution for beta, that beta equals to 140 degrees in size. This is angle beta equals to 140 degrees in size. The sum of the angles in any triangle is equal to 180 degrees. So in the green triangle BCD, 30 degrees plus 140 degrees plus this third missing angle is occurring in DBC, total must be equal to 180 degrees. Again, the green triangle DBC, 30 degrees plus 140 degrees plus the third missing angle DBC, total must be equal to 180 degrees. 30 degrees plus 140 degrees is 170 degrees plus the missing angle DBC, total must be equal to 180 degrees. Here we subtracted 170 degrees from this equation, and we found out that the missing angle DBC equals to 10 degrees. This is the missing angle DBC, that equals to 10 degrees in size. Our task is to find out the size of this big angle ABC, is equals to x. The size of this angle ABC is equals to x. It is this angle. This angle in total equals to 50 degrees plus 10 degrees, that is 60 degrees. 50 degrees plus 10 degrees is 60 degrees. So we found out that the missing angle ABC, the occurring angle x, is equal to 60 degrees in its size. So we finish with the first question. In the next step, I'll repeat on the solution of the second question on both methods. In the second question, our task is to find out the length of this side AD is equals to x. We have to find out the value of line segment x is equals to AD. So in the drawing, we have quadrilateral ABCD. We know that AB equals to BP. In addition, we know that those two angles are both right angles. And we know that this is the short line segment DP, this is equals to 1 unit in itself. This is line segment PC, that is equals to 4 units in itself. Again, our task is to find out the length of this side AD, that is x. We have to find out the value of line segment x. So, first of all, we join points B and D together by straight line. By joining points B and D, we divided this quadrilateral ABCD into two parts. The first part is this is the right triangle ABD. The second part is This is the arterial BDC. So in the next step, implement the Pythagoras theorem on both those two right angles. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this upper right triangle ABD, according to the Pythagoras theorem, BD squared, that is the square of the hypotenuse, equals to AB squared plus AD squared. And again, in the upper right triangle ABD, according to the Pythagoras theorem, BD squared, that is the square of the hypotenuse, equals to AB squared plus AD squared. BD is the missing hypotenuse, so relate as it is. And it equals to AB squared. AB is also the missing side, so relate as it is. It is AB squared plus AD squared. AD is x, therefore AD squared is x squared. So in total, according to equation 1, we should found out that BD squared equals to AB squared plus x squared. In the next step, implement this Pythagoras theorem on this lower right triangle DBC. According to the Pythagoras theorem, BD squared equals to BC squared plus CD squared. The lower right triangle BCD, according to the Pythagoras theorem, BD squared equals to BC squared plus CD squared. BD is the missing hypotenuse, so relate as it is, and it equals to BC squared. BC is also the missing side, so relate as it is, plus DP squared. DP in total is 1 plus 4, that is 5, therefore DP squared is 5 squared, that is 25. So in total, according to equation 2, we actually found out that BD squared equals to BC squared plus 25. This is according to equation 2. Well, according to equation 1, we only found out that BD squared equals to AB squared plus x squared. So we have two equations for BD squared, equation 1 and equation 2. Therefore, we created equation 3 that says that BD squared according to equation 1 must be equal to BD squared according to equation 2. BD squared according to equation 1 equals to AB squared plus x squared, and it must be equal to BD squared according to equation 2. BD squared according to equation 2 equals to BC squared plus 25. So in total, according to equation 3, we should found out that AB squared plus x squared equals to BC squared plus 25. But according to what is going to answer the question, AB equals to BP. AB equals to BP. Therefore, we substitute BP by AB. If PB equals to AB, it means that PB squared equals to AB squared, and it equals to BC squared plus CP squared. Yeah, actually, according to equation 3, we found out that AB squared plus x squared equals to BC squared plus 25. In the next step, we implemented the Pythagoras theorem on this right triangle PBC. According to the Pythagoras theorem, this right triangle PBC, PB squared equals to BC squared plus CP squared. Repeat again, the green right triangle PBC, PB squared, that is the square of the hypotenuse, equals to BC squared plus PC squared. PB is the missing hypotenuse, so leave it as it is, and it equals to BC squared. BC is also the missing side, so leave it as it is, so it is BC squared plus PC squared. PC is 4, therefore PC squared is 4 squared, that is 16. So in total, according to equation 4, we actually found out that PB squared equals to BC squared plus PC squared. But according to what is given us the question, PB equals to AB. So we substitute PB by AB. So PB squared is AB squared, and AB squared equals to BC squared plus PC squared. PC is 4, therefore PC squared is 4 squared, that is 16. So in total, according to equation 4, we actually found out that AB squared equals to BC squared plus 16. This is according to equation 4, but when according to equation 3, we only found out that AB squared plus x squared equals to BC squared plus 25. Now we can substitute AB squared, this equation 3, by BC squared plus 16 from equation 4. We did it, and we found out that AB squared equals to BC squared plus 16, and we have here plus x squared equals to BC squared plus 25. So in total, according to equation 3, we found out that BC squared plus 16 plus x squared equals to BC squared plus 25. Here we have BC squared on both sides of this equation, so BC squared will get cancelled. After cancel BC squared, this side of the equation we left only with 16 plus x squared, while on the other side of the equation we left only with 25. So in total, we found out that 16 plus x squared equals to 25. 16 plus x squared equals to 25. If subtracted 16 from this equation, we found out that x squared equals to 25 minus 16 is 9. So x squared equals to 9. Here we took out of this equation. We found out that x equals to the square root of 9, that is 3. So we found out that the length of this line 7 AD is equals to x is equal to 3 units. So we finish with the first method. In the next step, I print on the solution according to the second method. The second method, we did the construction, that is to say, we extended this side DC of the quadrilateral ABCD by 4 units. Repeat again, we extended side DC of this quadrilateral ABCD by 4 units. So CQ equals to 4 units in itself according to our construction. And DC is one side of quadrilateral ABCD, therefore it is absolutely a straight line. When you extend it side line by side line, the result DQ is also a straight line. So if you focus on the upper side of this straight line DQ at point C, here the sum of the areas must be equal to 180 degrees according to Rule 3. Rule 3 says that the sum of the areas from one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line DQ at point C? We have this angle that is the right angle, plus this missing angle, total the sum of those angles must be equal to 180 degrees according to Rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. The next step, we join points B and Q together by a straight line. By joining points B and Q, we can get the right triangle BCQ. So in the next step, we prove that those two right triangles can go into each other according to side angle side rule. So why those two right triangles can go into each other? First of all, those two sides are both equal to 4, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, BC is a common side that belongs to both triangles, so we can write down that BC equals to itself as a common side that belongs to both triangles. So if you prove that those two right triangles can go into each other according to side angle side rule. That is to say, we can prove that those two sides and the angle that is included between those two sides in this triangle PBC are also equal to those two sides and the angle that is included between those two sides in this triangle BCQ. Therefore, those two right triangles can go into each other according to side angle side rule. Again, we have those two sides and the angle that is included between those two sides in this triangle PBC are also equal to those two sides and the angle that is included between those two sides in this triangle BCQ. Therefore, those two triangles can go into each other according to side angle side rule. So triangle PBC congruent, this is the side of congruent to the right triangle BCQ according to side angle side rule. And from the fact that those two triangles can go into each other, we will grab that their corresponding sides must be also equal to each other and their lengths. The hypotenuse of those two triangles are the corresponding sides, and therefore PB equals to PQ. PB equals to BQ according to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, and therefore their corresponding sides, that is to say PB and BQ, must be also equal to each other and their lengths. But according to what is given as a question, AB equals to PB. So we can write here that AB equals to PB, and from this equation, we have that those three sides, AB, PB, and BQ, they are all equal to each other and their lengths. In the next step, we did the construction, that is to say, we draw a circle around this point B in such a way that point B will be the center of the circle and BA will be the radius of the circle. So this is the circle. BA is the radius of this circle, so we define the radius of this circle as R, so BA equals to R. And because of the fact BA equals to BP equals to BQ, BP and BQ must be also the radius of the circle that equals to R. what is the definition of a radius? The radius of any circle starts from the center of the circle and ends on the circle itself. That is to say, point A is located on the circle itself, or the circle passes from point A. For the same reason, the circle must pass also from point P and from point Q, because those are the ends of the circle. So in total, you can write down that the circle passes from points A, P, and Q. Okay. The circle passes from points A, P, and Q. It is given us a question. This is angle DAB, this is the right angle. That is to say, DA is perpendicular to AB. DA is perpendicular to AB. But AB is the radius of the circle. This equals to R. So you can write in that AB is the radius of the circle. This equals to R. From this equation, we will derive that DA is perpendicular to the radius of the circle. This equals to R. DA is perpendicular to the radius of this circle. This equals to R. Therefore, DA is a tangent to this circle at point A. Again, DA is a tangent to this circle at point A. DA is tangent to the circle at point A. So here we can implement tangent secant theorem in our drawing if we focus on this convex point D. Please click on tangent secant theorem. According to tangent secant theorem, if a tangent and a secant are drawn to a circle from the same external point P, this is the convex point P. From this convex point P, we have tangent P8 that is tangent to this circle at point A. Likewise, from the same convex point P, we have secant PC, and the external part of secant PC is PB, and the secant in total equals to PC. And according to tangent secant theorem, the following equation is true. The square of the tangent's lengths, that is to say PA square, equals to the product of the secant's whole length and its external part. The external part of this secant is PB, and the length of the secant in total is PC. So it is the product of the external part by the length of the secant in total. That is actually PB times PC. Or AP square equals to PB times PC. Again, AP square equals to PB times PC. So we can implement the tangent secant theorem in our drawing. If we focus on this convex point D, from this convex point D, we have tangent TA, tangent DA, that is tangent to this circle at point A. Likewise, from the same convex point D, we have secant DQ. The external part of secant DQ is DP. The secant in total equals to DQ. The product of the external part by the length of the secant in total is it is DP times DQ, and it is equals to DA squared. That is the length of the tangent squared. Or DA squared equals to DP times DQ according to tangent secant theorem. And again, according to tangent secant theorem, if we focus on the convex point D, the following equation is true. DA squared, that is the length of this tangent squared, equals to dP times dq. dP is the external part of secant dq, and dq is the length of the secant in total. So dA squared equals to dP times dq according to the tangent secant theorem. So dA squared equals to dP times dq. dA is x, therefore dA squared is x squared, and this equals to dP. dP is 1 times dq. dq is 1 plus 4 plus 4, that is 9. So in total, we actually found out that x squared equals to 1 times 9, that is 9. X squared equals to 9. Here we took out the equation, and finally found out that x equals to the square root of 9, that is 3. So we found out that AD equals to x is equal to 3 units in its length. So in both methods, we arrive to the same results. Okay, thank you very much.